Yes, I'm audible.
Sir. Yes, sir.
Yes, today topic is pericyclic. Yes.
Yes, sir.
Yes. Let me start basic application of pericyclic chemistry.
Yes, sir. It was a question.
Basic application of pericyclic reaction.
Oh, yes, yes. So the pericyclic reaction has a application in various synthesis or various organic synthesis which are useful in our daily life and in the research processes. So also, sir, apart from this, pericyclic reaction allows us to study the special type of reaction which does not have any intermediate in the formation during the formation of product, and it's allows us to study about the reaction which involves only heat and light, not any reagent to the product formation. Uh, Apart from this, pericyclic reaction such as Diels-Hilder reaction, so such reactions are considered as a following a green chemistry principle, that is, it follows a atom economy principle. So whatever reactant we are taking, we get the all the reactant atoms in the product molecule without any wastage or without any side product. So this is one of the major advantage of a pericyclic reaction, that we does not produce any waste product or a byproduct that can harm environment during the reaction processes. And also, sir, we does not need a large amount of reagents or a different reagent for a pericyclic reaction to proceed.
Yes, how many type of pericyclic reaction?
So there are 5 type of pericyclic reaction. One is the electrocyclic reaction. Second is a cycloaddition reaction. Second is I'm sorry, there is 4 type of reaction. So
Yes.
second is the cycloaddition reaction. Third is a sigmatropic reaction, and the fourth is a functional group
Group
transfer
transfer reaction.
reaction or
Group transfer reaction. Yes.
yes, group transfer reaction.
And cycloaddition is two type is in and cheleotropic.
Yes, sir.
Yeah, let me start first is electrocyclic. What the basic function of electrocyclic reaction?
So electrocyclic reaction allows us to study about the reaction that is involving polyene molecules. So it allows us to study the ring cyclization or ring opening of polyene molecules. So in reaction, we have a two type of mechanism. One is the ring closing mechanism, in which we have a polyene molecule. It undergoes a cyclization with at a cost of two pi bonds. We get a sigma bond in the product. And so another, we have a ring opening reaction, in which we have a cyclic molecule that that in presence of heat or light can undergo a ring opening. And we see that in place of a sigma bond, we can generate pi bonds instead, and we see the ring opening of the reactant molecule happens. Sir, it is the electrocyclic reaction are very much useful in the in stabilizing the mechanism of these type of reaction. And sir, it is also very helpful to study the reaction which involves the polyene molecules.
Yes. First basic things in electrocyclic is correlatory process and disorotatory process. Yes, what the basic difference?
Yes, sir.
And what the example?
Yes, sir. So, so conrotatory process is referred to the orbitals that is involved during the product formation. So, we have a polyene molecule, so we have a p orbital corresponding to these double bond or the pi bonds. So we have a p orbital. So during the process, the p orbitals it can rotate clockwise or anti-clockwise to form the product or to form the bonding between the p orbitals. And so according to the movement of this p orbital, we can refer whether it is a con-rotatory or a dis-rotatory. Suppose during the formation of a product, we have a p orbital which the two p orbitals move in a same direction, that is a clockwise or anti-clockwise. So then in that case, it is referred to the con-rotatory. While if we see that the orbitals are moving in opposite direction, that is, one is moving a clockwise or another moving anti-clockwise or vice versa. So in that case, the bond formation is referred as following a disrotatory pathway to the product formation. Sir, when we consider a case in which we have a, 6 pi system, 6 pi electron system, which under photochemical condition we see that it follows a con-rotatory pathway. And similarly, if we have a 6 pi system under the heat condition, that is, when we apply heat, it follows a disrotatory process. Sir, am I audible to you?
Yes, yes, yes. Good. Next, move on. FMO, frontal molecular orbital in ethene molecule.
Yes.
Ethene, 1,3-butadiene and 1,3,5-hexatriene. Yes, can you draw
Yes, sir.
on white paper?
Okay. Sir, I need to draw for ethene 1,3 butadiene only.
Yes, yes, ethene or 1,3 butadiene. Yes.
Yes, sir. Yes, sir.
Yes,
So
explain.
here is the for ethene.
Yes.
Yes, sir. So for ethene, we have a two carbon atom and we have a two molecular orbital, which is represented by Psi1 and Psi2. So when we fill up the electron, we will see that Psi1 is a HOMO and Psi2 is a LUMO. Now, when we draw the molecular orbital, we will see in terms of uh, uh, p, uh, p orbital lobes, we can draw it like so like this. We have a zero node in the Psi1 and while one node in the Psi2. So here we can see that the sign is changed in the Psi2 as a node is present. Now, sir, moving on to the 1,3-butadiene. So in 1,3-butadiene, we will have a yes, sir. So we will have a four orbitals, that is Psi1, Psi2, Psi3, and Psi4. And after since the butad 1,3-butadiene has a four electron, we will fill up the electrons. So we will see that the Psi2 is the HOMO and Psi3 is the LUMO. And when we draw the frontier orbitals, we will see that the Psi1 has a type something like this with zero node. That is all p orbitals are having a the one phase of a p orbital are present in a one direction and another in other. And we have a Psi2 like this, where we see that there is a one node which is symmetrical. That is the lobes that we have. This side is equal to that lobe we have that side. Only difference is that the sign of lobe is changed, and we have a one node in a Psi2. Now, sir, for Psi3 and Psi4, we will have something like this. Uh, Sir, it will be interchanged as the value of the Psi4 is greater. Sir, there was no space, so I have drawn here. So Psi3 will have two nodes, and sir, it will look something like this if we draw the different phases of the p orbitals. And Psi4 will look like this, and Psi4 will have a three nodes. So on the basis of energy, we can say that Psi4 is greater than Psi3, and Psi3 is greater than Psi2, and Psi2 is greater than Psi1. So this is the energy order. So we will see these lobe in the energy order. That is, first we will see Psi1, Psi2, then Psi3, then Psi4.
Yes. Yes. How many nodes present in ethene molecule in ground state?
Yes.
LUMO and HOMO. Ground state, excited state.
Sir, in ethane molecule, there is a zero. Yes, sir. Sir, there is a zero node in the ground state, while there is a one node in the excited state.
Yes. Next, move on 1,3-butadiene. 1,3-butadiene is ground state. How many nodes present ground state and excited state, LUMO and HOMO?
So can you please repeat the question?
Yes, 1,3-butadiene systems. How many nodes present in ground state and excited state, HOMO and LUMO?
Sir, am I audible?
Yes, you are audible now. Yes, are you getting my question? Yes, I am audible.
Yes, sir. Now you are audible.
Yes. Are you getting my question? Yeah, once again repeat.
Yes, sir. Please repeat the question.
Yes. How many nodes present in 1,3-butadiene system, HOMO and LUMO, ground state and excited state?
Yes, sir. Sir, when we see the thermal in thermal condition, we have a Schiffer 1,3-butadiene. In that, we have a one node. And when we talk about the LUMO, that is Chi3, we have a two node in the LUMO. And so in the case when we see the light, so then we will see that the excitation happens. And in that case, we will see Psi3 acts as a HOMO and Chi4 acts as a LUMO. So Chi3 will have a two node and Chi4 will have a three node.
Yes.
Sir, am I audible?
Yes, you are audible. And what the selection rule of
Yes.
electrocycling system? Selection rule for n and for n plus 2 system.
Yes, sir. Sir, in 4N system, we uh, we see that the whenever heat is there, in that case the conrotatory process is allowed while disrotatory is forbidden. And photochemical condition or a condition in which we apply the light. So in that case, we see that the disrotatory process is allowed while the conrotatory is forbidden. And when we talk about the 4N plus 2 system, in 4N plus 2 system, if we have a thermal condition, in thermal condition, the disrotatory process of a p orbitals is allowed, and conrotatory is forbidden. While in presence of light or photo condition, we will have that conrotatory process is allowed and disrotatory is forbidden.
Yes. Yes, good. Next, move on. Point 135 hexatriene system. Yes, how many nodes present in
Yes, sir.
ground state and excited state, HOMO and LUMO?
Yes, sir. Sir, I'll draw the system
Yes,
first.
yes, yes.
Do I need to draw the frontier orbital also?
Yes, FMO.
Okay, sir. visible to you?
Yes. Explain it.
Yes, sir.
Yes. Yes. Explain.
LUMO is the Shifur. Yes. Sir, am I audible?
Yes. Audible. Yes. Carry on.
Yes, sir. So, yes, sir. Sir, as I was talking, that Shi3 acts as a HOMO, and we will have a two nodes for the Shi3, and the Shi4 acts as a LUMO, and we will have a so when we draw the FMO, we will see something like this, that in a Shi1 or a ground, no, sorry, it is not a ground set, I'm so sorry. Sir, a Shi1 will have a zero node, and respectively Shi2 will have a one node that is at the center of the orbitals, and then we move further, that is Shi3, which is a ground state or a HOMO. So here two nodes. So I have shown those nodes with the dashed line. One is here and another one is here. So the nodes that are drawn will be symmetrical. That p orbitals changes with respect to the symmetry. And now, sir, for the LUMO or the excited state, we will have a Shi4, which has a three nodes in its orbital. Now, if we draw the three nodes, one will be here, another will be the here, and third will be the here. Again, sir, it is
Yes.
and one node is here and another is here. And sir, moving on to the last orbital, that is Shi6. Sir, this will have a five node, and sir, it can be represented as a midpoint of all the carbon-carbon bonds that are present in a hexatriene. That is, one is here, another is here, and then one is here, and another is here, and last one is here. So thermal condition. Sir, if we talk of photochemical condition, then we will see that the one of the electron get excited to the Shi4, and in that case, Shi4 is the and it will have three node in the and now, sir, Shi5 will act as a LUMO and it will have four nodes.
Yes. Good. Next, move on. Point number 2 is
Yes, sir.
cycloaddition reaction. Yes. What the basic application of cycloaddition reaction
Yes,
is
sir.
pericycline, how it is work. What the example of cycloaddition reaction? 2 plus 2 system, 4 plus 2 system.
Sir,
Describe.
yes, sir. Yes. So, so cycloaddition is a bimolecular type of a pericyclic reaction in which we have two molecules. One acts as a diene and another as a act as a dienophile. So this is if we take the 4 plus 2 case, and sir, if we take a 2 plus 2 case, we have a two dienes. So in this type of reaction, we have two unsaturated molecules with the pi bonds, and they interact with each other, or they form a transition state in which the electron transfers from a one molecule to the another, and we see a cyclic product is formed. So cycloaddition reaction has a wide application in the reaction synthesis and also in the retrosynthesis of a molecule. So in many pharmaceutical molecules, or in many organic molecule which has a impactful use for a human and for the laboratory processes. We see that the cycloaddition processes or specifically the Diels-Alder process acts as a one of the major reaction step in the process. So, cycloaddition reaction are the so cycloaddition reaction follows the atom economy, and so we does not see any byproduct or any waste that is produced during the reaction, and all the reactant atoms that is involved in the reaction, they are reflected in the product as well. So, if we talk about the types of the cycloaddition reaction, we have generally two types. One is a 4+2 reaction, and another is a 2+2 reaction. So, the 4+2 reaction occurs under the thermal condition. So, this is because of the selection rule that says that only the bonding orbitals which are formed by the supra interaction of the HOMO and LUMO of the two reactant molecule that are present. So if we when we see the bonding orbital, we see that it is only allowed under the thermal condition, while when we see for the 2+2 addition, we see that it is only allowed under the photochemical conditions. So 4+2 reactions are popularly known as the Diels-Alder reaction. It is named after the scientists who developed this reaction first. And so in this we have a diene and the dienophile. So diene refers to the conjugated molecule with two double bonds, and we have a dienophile, which is unsaturated molecule with some functional group, majorly electron withdrawing functional group attached to it. And we see the six-membered product is formed after the reaction goes, and we see a six-member ring with a double bond as a product for the Diels-Alder reaction or a 4+2 cycloaddition reaction. While in case of 2+2 addition, we see that the uh, ethene molecule or two molecule which has a double bond are present, and they cyclizes to form a product.
Yes. Intrafacial suprafacial system. What the basic difference in cycloaddition?
Yes. So, when we examine the formation of bond during the cycloaddition reaction, we see that the HOMO of one molecule interact with the LUMO of another. So, if so these interaction can be of the two types. So, if we see that the same phase of a that is involved in the HOMO of molecule interact with the same phase of a p orbital of a LUMO of another molecule. In that case, this type of interaction is termed as a suprafacial. While when we see that the HOMO of one molecule has a different phase with what we have for the LUMO of another. So that is, if we have a plus of one orbital, suppose it is a LUMO, and we have a plus of so we have a minus of another molecule, then sir, during the interaction we will see that this type of interaction does not leads to the bonding, but it leads to the anti-bonding interaction. In that case, this type of interaction will be termed as a intrafacial.
Yes. Yes, what the selection rule of a cycloaddition reaction?
The selection rule for cycloaddition reaction first is the interaction between the homo and LUMO of diene and dienophile. It must be supra interaction. And so another selection rule is that the reaction must occur in when we have a thermal condition. And sir, as in photochemical condition, we will see that there is a supra intra reaction, not supra reaction for the diene and dienophile interactions.
Yes. Yes, first example is cycloaddition is Diels-Alder reaction. Yes. What the product of Diels-Alder reaction? And reactant it react
Yes,
with
sir.
the diene and dienophile. What will be the product? Exo and endo.
The, so the product in the majority of the reaction is a endo product, and sir, but in some cases we see there is a possibility of exo product. So the reason for this is the interaction that occur during the formation of the product. So we see that there is in the transition state there is an interaction that occur between the p orbital of a diene molecule and the p orbital of the dienophile. And if we have some attached group to the dienophile, then we see that attached group also interact with the p orbital of the or the second p orbital of the dienes that are present, uh, uh, and the p orbitals of the groups that is attached. So in that case, we see that there is a two interaction. One is referred to the primary interaction that leads to the formation of bonding, and another interaction is only to stabilize the transition state, which are referred to as a secondary interaction. So in endo product, sir, in endo product, we see this type of interactions occur, that is primary and secondary, which is why the endo product are referred as a major product, or although it is kinetically favored product. While in so when we see for the exo product, which is a thermodynamically favored product, so in that case only one interaction is present, that is the primary interaction, which leads to the product formation. And due to this, the transition state is not much stabilized as comparison to the previous one. So which is why exo product are termed as a minor product.
Yes, Diels-Alder reaction is stereoselective, stereospecific, and regioselective. This type of reaction.
Yes, sir. So, Diels-Alder reaction are stereo-specific reaction. That is, whatever stereo we see in the in a diene and dienophile in the product. So, suppose we have a diene with the cis stereo, then in the product molecule we will see that the position of the two bonds that is present cis to each other. So that will be same in the product. And while if they are trans in the product also, they appear to be trans to each other. And sir, this can also be fully explained with the transition state that is formed in during the secondary reaction, during the secondary interaction. I'm so sorry.
Yes, good. Next is dienophile is a present of electron withdrawing group, and diene is presence of electron release.
Yes, sir.
So what will be the product? Possibility
Yes.
of exo endo.
So endo product will be the major product in this type of reaction. Sir, as diene has an electron donating group, so in that case, sir, we see that it only stabilizes the homo of the orbitals, and when we see the transition state, so we can see that the electron withdrawing group and the p orbital that is involved can stabilize each other with the interaction of a p orbital with the orbitals of the electron withdrawing group. And similarly, sir, we can see that there is a interaction between the p orbital of pi bond with of a dienophile with the p orbital of a diene.
Yes, good. Next is cyclic diene and compared to acyclic dienes, which will more stable. What the rate of these one? Rate of reaction?
Yes, sir. So, if we see cyclic diene, sir, in that case, the rate of reaction will be very high as comparison to the acyclic diene. Sir, this is because, sir, in the during the reaction, we need a cis stereo, S-cis-oid stereo for the diene to be present. So, as we form a cyclic transition state, so when we have a S-cis-oid form, in that case, the interaction with the dienophile is much easier as the double bond are in the proximity of the reaction. So which is why it is much favored to have a cis S-cis-oid form for the diene. So in cyclic case, what we have is the proper S-cis-oid form. That is, the molecule cannot undergo any rotation to the transition to the transform, or there is no sort of distortion from this cis form. And so when we talk about the acyclic diene, sir, in that case, there is a single bond present which can easily be rotated under any under any heat condition, as the rotation barrier for the single bond is not much, and we see that the cis transition cis form can be transition into the transform and vice versa. So which is why the rate of the acyclic form is lesser as comparison to the cyclic form.
Yes, good. Yes, electrocyclic and cycloadhesions. Let's complete.